Hello and welcome to day 15 of Python Challenge. Today we're going to talk about SQL. So without further ado, let's get started. So for all the training and practices for this chapter, we need to install a free software which is called uh, SQLite. That's DB browser for SQLite. That's for free. You can download it for free from this link in the presentation. So really quick preview about the SQL and databases. So when the computer industry started in 60s and 70s, the only way to have data stored was to have them stored sequentially, meaning that we probably needed a tape, some kind of a tape, and the access was only sequential. So we can imagine how updating those databases would have been difficult because we had to get to that exact point that we needed to, and for to get to that point we had to play that database or play the tape that had the database on uh, to get to that point, and we had to write new data or update the data from that point onwards. So that was of course very challenging, and pretty soon as the data grew, we needed a new model to store the data. So the technology that came around was the random access. So we didn't need to wait sequential. We didn't need to wait sequentially to get the to that point of data that was our interest. We could get it by random access. When we get that random access, the new model for database was called relational database. So relational database was what brought the power to deal with a large amount of data and efficiently retrieve it and manipulate it and store it in the way that we wanted to. So the terminology that we have here is database, which is contain many tables. We have relations or tables, which is the tuples and attributes. We have tuples or rows, which is a set of fields that generally represent an object, like a person or music track. And we have attributes, also known as column or fields, which is one of the possibly many elements of data corresponding to the object represented by the row. So this is one of the uh, example of a database. So we have a column called title, we have a column called rating, length, and these are attributes of music records. So title, rating, length, they are not part of the attributes, they are just metadata, and whatever we have below them are the actual data that needs to be stored in the database. So stands for SQL stands for structured query language. Uh, the command that we use in SQL are either create, retrieve, update, or delete. So here we can see like an overflow of how we can manipulate data using Python. So we have our input file. Usually with Python we can clean the data. The data has a lot of information that we probably don't need, so we can clean it. Python can work directly with the database file. and the database file also have uh, communication with our SQL database program. In this case, it's going to be SQLite browser, and we, as a person who is interested in those data, can interact with Python and with the SQL program. The output of what we have or what we need can be represented through R, Excel, or JavaScript coming from Python program. We can also have web application with databases. So the application developer builds the logic of the application and monitor the application for problems. Database administrators also monitors and adjust the database as the program runs in production. And both of these people are participate in the building of the data model. So again, here we have the application software interacting with end user and database server, and the database servers interact with the database tools. We have the database administrator communicating with the database tools, and we have the developer and end user interacting with application software. So again, the database administrator is the person responsible for designing, implementing, and maintaining and troubleshooting the database in one organization. And we talked about the database model. Database model, also called database scheme, is the structure or format of a database that within a company or in a structural organization, we agree to follow these rules. So it's a formal language supported by the database management system. A couple of very common database systems is Oracle, MySQL, SQL Server by Microsoft, and the program that we are using here, which is called SQLite. Also, SQLite has been implemented and is being used by a lot of other software, including the Python. So SQLite browser is a pretty popular database software. It's free and it's pretty small. We can download it from this website here, sqlitebrowser.org, and SQLite is also embedded in Python and a number of other programming languages. So this is how the SQLite looks like. And the first exercise is going to be creating a database. A cheat sheet of all the command lines, all of the commands that we're going to use in this exercise is in this link that is in the presentation. So we're going to use the SQL language, and the create command is as below. So create table. The name of the table is users in this case. We have two fields. We have name and email. Both of them are character up to 128. So if we copy these commands and put it in the SQLite, we just need to press the run, and after that we will have our table of users that has names, and email, that both of them uh, accept character up to 128 characters. So we can fill our little table here with the name and email addresses. Again, SQL data SQL has four main commands: create data, retrieve, update, and delete. Now, we already created this table. We're going to use the insert to update the table. So the format is insert into. The name of the table that we have is user. We're going to fill out the name and email portion of it, and the values that we're going to put is here, which is Christine and the email address of Christine. After putting that command here, we just press the run or play here, and we will see that the Christine has been added to the end of the table that we have. Now we're going to look at the delete. So for delete, the format of delete is delete from the name of the table. In this case, it's going to be user, and we have a var clause, which the email is identical to a specific email address, in this case Ted. So after running this command, we will see that Ted's name and email address has been deleted, which previously was on row number 4. Now we're going to use the update. So we're going to update the table, in this case users. We're going to update the name to Charles, where the email is csev at umich.edu. We put it in the SQLite database browser, and we see that the name, we see that the email address has been updated. So for retrieving the excuse me, for retrieving the records, we use select. So the format of this feature is select. In this case, we're gonna select star, which is everything, from name of the table, which is users, where the email is this specific email, and yeah, in this case we select everything from users where email is identical to this. In this case, the first example is select stars from users, which will bring us everything, and the second one is a more specific select the star from users where email address is equal to a specific email. In this case, it's just going to be this row. We can use the order by. The first example is going to be select star from users, order by email. So in this case, we're just going to have all the users which are sorted by the email address. And the second example is the same thing, select star from users, order by name. In this case, we're just using name, and the name is going to be descending. So the first example, again, select everything from users, order by email. So we see that the email is being ascending. So the letter A is the first. We don't have anything with B, but C, we have two things with C, and then going in the ascending order. by email. So just a summary, we uh, learn how to insert to the users. We learn how to delete something from the table. We learn how to update some characteristics of users. We're able to select everything from users. We were able to select specific details, either in this case by email, or in this case again by email, by by all the emails, sorting by all the emails, and with the order of ascending based on the email address. So this is uh, basically, by this time we might think that what's very exciting about this thing, SQL. And we have to remember that the power comes when we have a lot of tables and a lot of data, and that's where we can see the power of SQL. So now we're going to talk about complex data models and relationships. So uh, designing a database is a art form, and it needs a lot of experience. What we want to do is to avoid the uh, design flaws and create a clean design that is easily uh, understandable for others, and uh, other people can also fine-tune the database based on their needs, of course. And we have to have a clear picture at the beginning of the design to know what we're gonna be designing, basically. So this is like a example of a calendar. So we have events, we have participant, we have the persons, we have locations, and we have occasions. In this case, you see that we have we connected the tables with arrows. In one end we have one arrow, and the other end we have two arrows. So when we have two, it means that we have many relationships. When we have one, it means that we have one relationship. For example, here we have a one to many relationships between events and locations. Here we have one to many relationships between events and participants, for example. So this is how um, we can understand the number of arrows. So it's just one to many relationship or many to one relationships, depending on which direction we read this relationship. Again, this is a big picture of how, for example, a company design its database. So again, we have to have a big picture when we want to design a database. So now we're gonna talk about building a data model, drawing a picture of the data objects for our application, and then figuring out how to represent the objects and their relationships. The basic rule is don't put the same string data in twice. We have to use a relationship. And when there is one thing in the real world, there should be one copy of that thing in the database. So this is an example of creating a music track management system. So we have a track name, we have the length of the track, we have the name of the artist, we have the name of the album, we have the genre of the music, the rating, and the number of those tracks. So Now we have to have an identity for each piece of information. So is the column an object or an attribute of another object? So we have to identify that. Once we define object, we need to define the relationship between the objects. So in this case, we know that we we have track, we have album, we have artist, we have genre, we have rating, we have length, we have count. So the first thing that we can think of a track is, so the track has an album, uh, it belongs to an artist, and it has a genre. So it also has a rating, it also has a length, and it also has a count. So we're gonna create uh, an identity called track with these three attributes: rating, length, and count. Now the track identity, uh, I'm sorry, the track entity connects to album. So the album also connects to another entity, which is the artist. So the track belongs to album and the album belongs to artist. The track also belongs to a genre. So that's how we can separate our entities and connect them in a way that we can retrieve data later on or update data later on. Okay, now we're going to talk about representing relationships in a database. So there are a lot of rules for representation and basically theory of database. We're going to mention a couple of important ones. The first one is that we should not replicate data. So we should have a reference data and always point at that data. We should not have it duplicated. And the second rule is use integers for keys and for references. So that's important. We always want to have integers, unique integers for keys. And the other rule is add a special key column to each table, which we will make reference to. So basically, by convention, many programmers call this column ID. So for example, if we want to keep track of which band is the creator of each music track. So the pink color is represented at what album does the song belong to. So the pink is basically the notion of creator in this example. And we want to know which album this song is related to. So we're gonna use the ID in this case. So this is gonna be the name of the artist, and this is gonna be the table for the name of the artist, which has the ID and names. So we have 1, 2, 3, or based on how many artists we have the ID number for them, and in the other column we have the name of that artist. In the album uh, table, we have the ID for the album, we have the artist ID, which is a foreign key pointing to the artist, and we have the title of that album. And in this case, we use this integer to identify the artist in the artist table. Okay, so basically we are gonna need three type of keys. The first one is the primary key, is generally an integer, which is auto automatically incremented, and it's unique at each table. We have a logical key, and logical key is the way that we uh, present that key in the uh, outside world. For example, the title or the album is a logical key. And finally, we have the foreign key, which is uh, an a key that is pointing to another table. So the best practices that we have for the keys are: never use your logical key as the primary key. Logical key is basically what we call it outside the database. Logical keys can change. Uh, for example, the the email address of the email address cannot be a good primary key because we change email address, we get the new email address, so it cannot be a good primary key. And the other rule that we have is the relationship that are based on matching string field are less efficient than integers. So we always want to have an integer to create a relationship between two or more tables. So for foreign key, uh, the rule that we are using here is we use an underline to underline ID basically. Um, so basically the name of the table and underline ID is the rule for creating a foreign key in another table. So if I have a table called artist, the foreign key for that table is artist underline ID. And when all the primary keys are integer, then all foreign keys are integer. And this is what we want in a design of a database. We want all primary keys to be integers as well. So now we're gonna build a relationship. So again, going back to our music track inventories database, we have tracks that belongs to album, album belongs to artist, and track also belongs to genre. So using the primary key concept, uh, each table has a primary key. Using the foreign key concept, we use the table underline ID as a foreign key and point it to that table. And we have the logical key, which means that the way that we know that information outside the database, in this case is going to be title. So in this case, the track, title, rating, length, and count, they all belongs to album because we were able to connect the track um, table to the album table by using a foreign key. So all the attributes in the track can be related to the albums as well. Uh, Here is the implementation of the design that we had. So the track connects to album using the album ID, track connects to genre with the genre ID, and album connects to artist using the artist ID foreign key. Um, in this case, we are creating artist table. So the ID is the integer, which is primary key. So it cannot be null. It is primary, and it automatically increases. and it is a unique to that table. It is a unique value to that table. And yeah, so that's the command that we use in SQL. It will create the table genre. It will give it a primary key ID, and it will give it a name as a logical key. We do the same for album and track. For album, we have a primary key. We have a foreign key to the artist table, and we have a logical key. The same for the track, primary key, um, logical key, two foreign key to album, one to album and one to genre table, and we are using some other attributes like length, rating, and count for the track table. So after we put all of those information, this is what we get. We have the album with ID, artist ID, title. We have artist with ID and name. We have genre with ID and name, and we have track with ID, title, album ID, genre ID, length, rating, and count. Now we're going to populate this information, this table with below information. For example, insert into artist name value Led Zeppelin, and we do the same for AC/DC. So we are populating the artist table. Uh, when we do that, if we do it in the SQLite, after we run the run or play button, we see that the table artist is populated with those two names. Um, in the genre table, we update the genre name with rock and metal, and the album table gets updated by who made who. The artist ID is 2, and uh, the name of the title is Roman numeral 4, and artist ID is 1. So now we're gonna populate our track table. We're gonna say the order of the table, which is going to be populated, which is going to be title, rating, length, count, album ID, genre ID will be populated with this information, and the rest of the table will be populated by this information that we are going to put. So it's going to be the title, rating, length, count, album ID, and genre ID. So here we can see that the track table has foreign key as album ID connecting to the album, and genre ID connecting to genre table. Album table also connects to the artist table using the artist ID foreign key. So now we're going to talk about using join across tables. So the power of relational database is that we can mix and match information from different tables, and we do this specifically using the concept of foreign keys. So the join operation is like basically links is like a link between several tables, and we use the join special character, special word basically, and we can use the on word to specify which characteristics of two or more tables we want to join. So for example, in this case we have album and we have artist. The album has a foreign key to the artist table. Now we're gonna join the album and artist together. We're gonna choose album title, which is this column, and we're gonna choose artist name, which is this column, from album and artist, which are joined together. And their join criteria is the album.artist ID is identical to artist ID. So where the artist ID is identical to the ID, we're gonna get the album title and we're gonna get the artist name. So basically the first part of the select is what we want to see. The second part is the tables that hold the data, and the third portion is how these tables are linked. So in the previous example, we had artist ID as a foreign key. So in this case, we match the rows that have identical IDs, artist ID and IDs, and this is going to be the join criteria, and our final result is going to be title and name, where the title corresponds the name of the artist. The other example is where we don't use the on clause. So in this example, we use the track title, track genre ID, and genre name from track and genre. So basically, we see two tables, track and genre has been connected to each other. In this case, we don't see any. We see some genre ID matching ID here. For example, here they do match. Here they don't match. Here they do. They do not. They do not. Here they do. And this they do not. And here they do. So if we don't have the on clause, basically this join command is gonna be connecting two tables without any criteria. So basically that's not what we want. That's not what we want most of the time. So the next example is going to be select track title, genre name on track, and genre, where the track genre ID equals to genre ID. So in this case, we're gonna have track title and genre name from track and genre, where the genre ID in the track matches the genre ID in the genre table. So this is going to be the end result of this select. Another big one, we're going to take the track title, artist name, album title, and genre name from track, genre, album, and artist, where the genre ID and the track identicals is identical to genre ID, and the track album ID identicals to is identical to album ID, and album artist ID is identical to artist ID. So that's going to be the uh, output of that select statement. Now we're going to talk about many to many relationships. So uh, in this case, so we have we talked about that, for example, one track or many tracks belongs to one album. So this is many to one relationship. Now, so for example, many children can have one biological mother, or when many genre ID uh, belongs to one genre name. But we have some situation that we have many to many relationships. For example, many authors can have many books, or many books can be written by many authors. So we don't have necessarily the one to one or one to many relationships. Um, and it's very difficult to uh, to save this information unless we have a joint table which has both the name of the author and the name of the book, and it can keep the name of the author and name of the book by using the primary key from each table. For example, uh, going to learning management system and LMS, a student can be a member of many course. So basically, many students can be member of or registered for many course, and many courses can be assigned to many students. So again, we have a many relationships. In this case, we have a user table with ID, name, email, and we have a course table with ID and title. We have the membership relationships table, which has the primary key from the user and the primary key from the course. So this table in the between doesn't have a primary key. It uses the primary key of the both tables that are going to be connected to in a many to many relationship. So in this case, we're going to create a table user, a table course, and a table member with the primary key coming from both uh, user and course tables. So this is going to be the output of the previous commands that we put in SQLite, and now we're gonna populate it. So we're gonna insert into the user the value of name and email, these three, and we're gonna populate the course with three courses. Basically, we have Python, SQL, PHP. So this is going to be the output of the previous commands, and now we're going to populate more information. We're going to populate the member table with below values, and basically if we go back here, so the member has a user ID and course ID and a role. So, and the primary key is the combination of the user ID and course ID. So uh, when we come to the member, so we have a user ID, we have a course ID, and we have a role. And I believe the role 0 is the student and 1 is teacher. So that's going to be that's going to be the output of previous insert. And now we can select username, member role, and course title from user and member. So that's user and member. And course and member user ID identical uh, it's identical to user ID, and member's course ID is identical to course ID and will be ordered by course title, member's role, and the descending, and username. So that's going to be the output of that select. So this is a website done by the Mr. Charles Severance as easy. I apologize, this might not be for Mr. Severance, but this is a website that you can create your relations between your tables online on an easy way. So basically, uh, by using the complexity uh, of the complexity of the commands that we used uh, help us to have a speedy retrieval or updating of data. It may looks complex, but this complexity will help us to manage a large amount of data. It will help us to be able to grow methodically and be able to manage data growth properly. And also, uh, the amount of time that will be consumed to retrieve data or update data will be drastically decreased also. So there might be a trade-off between the complexity of the codes that we write, but the more complex it is, it will be easier for the database to be maintained and managed, and the faster data will be retrieved. So we talked about the indices, we talked about the constraint, and we talked about the transactions. So basically, the indices are improved access performance for things like string fields, constraint on the data. For example, some data cannot be null, or they are unique, or they are automatically increased. And the transaction is like allow a SQL operation to be ground up. To be grouped and done as a unit. So we talked about the relational database will allow us to scale to very large amount of data. The key has to have one copy of any given data and use that relational language to connect the different copies together. and this will reduce the amount of data, and it will reduce the amount of time that is needed to store and manage and retrieve data. And the whole of this process is an art. So we need to be an artist, or the database administrator needs to be an artist to do all of that properly. So that's all for today's presentation. Of course, we have to give acknowledgement to where it's due. This presentation was done by Mr. Charles Severance. I hope this has been informative for you, and thank you for listening.